500 years ago, the Aztec civilization in today's Mexico believed that the sun and all its power were sustained by blood from human sacrifice. Thankfully, nowadays we know that the sun, along with all of the other stars, are powered by a reaction called nuclear fusion. This reaction releases great amounts of energy. If nuclear fusion can be replicated on Earth, it could provide virtually limitless, clean, safe, and affordable energy to meet the world's energy's demand. So how exactly does nuclear fusion work? What are the challenges? And more importantly, when can we expect to have operational nuclear fusion plants? Watch the video till the end to find out. And make sure to power up that like and subscribe button if you like videos about technology and innovation. How does it work? Simply put, nuclear fusion is the process by which two light atomic nuclei combine to form a single heavier one, while releasing massive amounts of energy. Fusion reactions take place in a state of matter called plasma, a hot charged gas made of positive ions and free-moving electrons that have unique properties distinct from solids, liquids, and gases. Stars, including our sun, are balls of plasma made of hydrogen and helium created by the gravitational collapse of clouds that contain cold gas, which is compressed and heated, becoming plasma. This all creates the perfect conditions, including the high temperatures of around 10 million degrees Celsius required for hydrogen fusion. These high temperatures provide enough energy for light nuclei to overcome their natural electrical repulsion, so that once they come into very close range of each other, the nuclear force that attracts them outweighs the electrical repulsion known as the Coulomb force, allowing them to fuse, as well as the heat and close proximity fusion requires the nuclei to be confined in a small area. The extreme pressure created by the gravity of stars create this final requirement for fusion to occur. When protons and neutrons are combined from lighter nuclei by this nuclear attraction, the nuclear reaction releases extra energy. This is not the same for heavier nuclei, which have a shorter range nuclear force, which instead of releasing energy with fusion require energy as an input. How to induce nuclear fusion artificially? With the right amount of heat, proximity, and high levels of pressure, protons and neutrons can be forced together, releasing different levels of energy depending on the makeup of the element. So far, we have looked at the fusion that occurs in stars, but scientists and engineers have been trying to recreate the conditions for fusion here on Earth. The massive gravitational pull of stars helps to induce fusion, but without this force, higher temperatures are required to cause fusion. For example, on Earth, temperatures over 100 million degrees Celsius are needed to cause fusion between deuterium and tritium. The amount of energy produced from fusion is vast, 4 times as much as nuclear fission reactions, and fusion reactions can be the basis of future power reactors. Plans call for first-generation fusion reactors to use a mixture of deuterium and tritium, heavy types of hydrogen. In theory, with just a few grams of these reactants, it is possible to produce a terajoule of energy, which is approximately the energy one person in a developed country needs over 60 years. Advantages of nuclear fusion. Scientists and engineers have been investigating how to replicate and harness nuclear fusion on Earth at an industrial scale. The benefits of fusion fuel include providing a fully renewable, clean, safe, and affordable source of energy. As mentioned previously, nuclear fusion is efficient, 4 times more efficient than fission per kilogram, and nearly 4 million times compared to the amount of energy produced from burning coal or oil. Not only does fusion have the potential to provide nearly limitless clean energy, but it also is a cleaner source of energy that, unlike fission, doesn't produce long-lived nuclear waste. Because of this, there's no danger of radioactive contamination and fallout as a result of a meltdown. Should there be an accident, the plasma will terminate and lose its energy very quickly before any sustained damage is done to the reactor. Finally, fusion doesn't emit any carbon dioxide or other harmful greenhouse gases into the atmosphere, providing a source of low-carbon energy too. Methods to contain high-temperature plasma. 2 main methods are being investigated for containing the high-temperature plasma required for fusion reactions on Earth. These are magnetic confinement and inertial confinement. Magnetic confinement. This method uses magnetic fields to hold the plasma in place. The plasma is usually held inside a ring-shaped chamber called a torus, with powerful magnets placed around the inside edges. The magnetic field keeps the hot plasma in the middle of the chamber and away from the edges. The plasma can also create its own magnetic field as it flows, which can also be used to further contain the plasma itself. This method has been successful within machines known as tokamaks that can create the required heat, particle density, and energy confinement to create a fusion reaction. Inertial confinement fusion, or ICF. ICF uses compression rather than high temperatures to begin the fusion reaction. Compressing the fuel for short periods of time measured in nanoseconds increases the implosion speed and creates shock waves that heat the center of the cooled plasma. This shock heat initiates the fusion reaction that releases energy. This method uses the same process of collapse, compression, heating, and subsequent nuclear fusion as used in thermonuclear weapons. Stars also use a similar set of processes, except these are caused by gravity, causing the stars to collapse, heat, and expand once more to reach an equilibrium between size and temperature. The most common technology used to create this type of fusion on Earth are high-powered lasers, although particle accelerators have also been used. Research into this process using lasers in very short bursts to initiate fusion has been taking place at facilities including the Laser Megajoule in Bordeaux, France, and the National Ignition Facility at the Lawrence Livermore National Laboratory in Livermore, California, US. Challenges. For one thing, materials will be needed that can withstand the assaults from products of the fusion reaction. Deuterium fusion reactions produce helium, which can provide some of the energy to keep the plasma heated, but the main source of energy to be extracted from the reaction comes from neutrons, which are also produced in the fusion reaction. The fast-flying neutrons will pummel through the reactor chamber wall into a blanket of material surrounding the reactor. Not only will the neutrons deposit energy in the blanket material, but their impact will convert atoms in the wall and blanket into radioactive forms. Methods also will be needed for confining the radioactivity induced by neutrons, as well as preventing releases of the radioactive tritium fuel. In addition, the interaction of the plasma with reactor materials will produce radioactive dust. Building full-scale fusion-generating facilities will require engineering advances to meet all of these challenges, including better superconducting magnets and advanced vacuum systems. The raw materials needed as fuel for the reactors also prove to be an obstacle at this moment. While it is true that deuterium is cheap and plentiful, tritium, however, is rare and comes in at $30,000 per gram. With technological advancement, fusion reactors should theoretically be able to breed tritium, but an operational nuclear fusion reactor is required to jumpstart the process. Until then, will we have enough tritium? Future of fusion technology development. As the world population grows, there will be a growing need for energy. Nuclear fusion research has been conducted in over 50 countries over the past decades with varying levels of success. The future of fusion technology development and speeding up the rollout of nuclear fusion as a viable energy source relies on global collaboration. Practical solutions to the hurdles need to be developed, validated, and qualified alongside the development of supporting infrastructure and standards. Currently, full power experiments are due to start at the ITER project in France in 2036, with a date of 2050 for the realization of an operational electricity-producing fusion power plant. Alongside government-led research, there is also a growing number of privately funded commercial enterprises that are drawing on and expanding the decades of publicly funded research into fusion. These privately funded organizations are hitting at a date later than 2050 for the first operational fusion nuclear energy plant. Thank you for watching this video. Don't forget this video a thumbs up. And let's power up that subscribe button in 5, 4, 3, 2, 1, boom. Do you think we will have a fully operational nuclear fusion plant before 2050? Let us know in the comment section. We'll be back with another nuclear video soon. Check the video on the left or right to watch our latest videos. Peace out.